How do you build a system you can actually trust to control the power of a star right here on Earth? It's easily one of the greatest engineering challenges of our time. But what if the biggest problem isn't the hardware, the magnets or the incredible heat? What if it's the very language we use to tell the machine what to do? Today, we're going to dive into a pretty radical new solution, a universal mathematical language that's designed to build provable trust right into the core of our most critical technologies.
All right, so to really get why we need this new language of trust, we first have to wrap our heads around the absolutely brutal, frankly insane environment inside a next-generation fusion reactor.
I mean, this is really the question, isn't it? We are talking about containing plasma that is hotter than the core of the sun. And doing that safely, reliably, for long periods, it requires a level of control that pushes the absolute limits of engineering, of physics, and of computer science.
The conditions in there are just staggering. See, unlike current experiments that might last for a few seconds, future reactors like ITER are being designed to run for over 15 minutes at a time. The sensors that control the plasma are just getting blasted with intense heat and radiation, and they have to provide perfect, constant measurements second after second without a single failure. Any tiny drift, any error, could be catastrophic.
And this data right here, this really paints a picture of just how extreme net heat is. In a worst-case scenario, without any active cooling, a critical magnetic sensor would hit 845 degrees Celsius. To put that in perspective, aluminum just turns to liquid around 660 degrees. And even with a state-of-the-art cooling system, it's still running at 450 degrees. This is the harsh physical reality the control system has to deal with.
So we have this immense hardware challenge. But let's say we solve it. That's when we uncover an even deeper problem, a crisis not of engineering, but of trust in the very models we use to control everything. You see, even if our sensors are absolutely perfect, they feed data into a computer that's running on a mathematical model of the plasma. And that model, well, it has to be a simplification of the incredibly complex, chaotic physics that are really happening inside that reactor. And this creates a very dangerous gap.
And this is the core of the issue. On the left, you've got the model that the controller sees. It's a clean, simplified mathematical proxy that the computer can govern perfectly. But on the right, that's the actual messy, physical reality of the plasma. And those two things, they are not the same.
This quote from the source material is honestly, it's chilling. What it means is that the control system could be perfectly following its own rules, reporting that everything is A-OK, while in the real world, a dangerous instability, this physical island, is growing completely undetected. This is that gap where trust completely breaks down.
So how in the world do you bridge a gap like that? The answer that's being proposed here isn't just, a better piece of software or a slightly better model. It's a fundamentally new kind of mathematics, designed to formalize the very idea of governance and trust itself.
It comes from a field called category theory, and it's called the category of coherent spaces, or just CO for short. Now, try to think of it less as a program and more like a mathematical operating system for creating systems you can prove are behaving correctly. It's basically a universal rulebook for any system that needs to follow rules.
The way it works is pretty elegant. It has three core concepts. First, you have the jurisdiction. That's all the possible states the system could ever be in. Second, you have the law. That's a rule that basically assigns a penalty score for being in a bad state. And third, you have the judge and jury, a verifier that checks cryptographic receipts to make sure every single action taken is legal. And look, this isn't just a fun analogy, it is backed by some seriously rigorous mathematics. All those symbols you see on the screen, that's what formalizes the concepts we just talked about. You can even see the core components right there. The X for the jurisdiction, the V for the law, and the RV for the judge and jury. This is what turns a simple idea into a provably trustworthy framework.
Okay, so this abstract legal system sounds cool, but how does it actually control a fusion reactor? Well, the key is a concept called the receipt. So here is the crucial point. In a CO system, absolutely nothing happens without a paper trail. Every single action, from adjusting a magnetic field to updating some internal budget, has to generate a digital receipt. Think of it as an unforgeable piece of data that serves as proof that a legal step was just taken. This right here is the system's golden rule. There is no such thing as an action that is secretly or implicitly legal. If the verifier can't check a valid receipt for it, then the action is illegal, period. It forces every single part of the system to show its work, all the time.
And these receipts aren't simple. They're incredibly detailed. They contain the identity of the system and the exact policy it's following, a cryptographic link to the previous receipt, which creates this unbreakable chain of evidence, and the specific claims being made, like, I just spent this much energy, or my risk level is below this specific bound.
This quote really gets at the core philosophy of the whole thing. The system isn't designed to be perfectly exact. It's designed to be perfectly safe. It will always, always err on the side of caution. It would much rather be a little too conservative in its estimates than allow even a tiny chance of something dangerous slipping through that gap between the model and reality.
And this is what brings it all together. This entire mathematical framework is actually being implemented using what are called formal proof assistants, basically software that can check mathematical proofs for correctness. They are literally building a tower of trust, where each layer is mathematically proven to be sound before the next one ever gets added on top.
Now, this is where it gets really, really exciting. This whole system, this entire language of trust, was designed from the ground up to be so much bigger than just fusion.
You see, the mathematics of states, laws, and receipts, it doesn't actually care if it's governing superheated plasma or a self-driving car or an AI. The underlying structure is completely domain agnostic. It's universal by design.
I mean, just think about the possibilities here. You could use this exact same framework to make sure an AI system is operating within safe, verifiable bounds. Or you could use it to govern autonomous robots, high-frequency financial trading algorithms, or the control systems for our most critical infrastructure. It's a universal blueprint for building systems we can actually trust.
This single sentence from the specification says it all. The whole goal is to create a system where you can build complex, governed systems from smaller, proven parts, where every single action is deterministic and can be verified through a crystal clear trail of receipts. It's a kind of governance that can actually scale.
And all of this leaves us with a final, powerful question. The immense problem of trusting a fusion reactor forced the creation of a new, more rigorous language of control and trust. So now that we have it, the most important question might no longer be, can we control our most complex technologies, but rather, how will we choose to govern them?